Hello dear students, in today's lecture we will try to solve some numerical problems based on Debye shielding and plasma frequency, etc. So, these numerical problems will help us understand the concept better and also increase your problem solving ability, right. So, as we know, plasma is considered as a neutral entity. We refer to it as the quasi neutrality of plasma, where within a very small microscopic regions, there can be some disparity between the number of electrons and ions, but as a whole the entire plasma has equal number of electrons and ions. So, this idea is called as a quasi neutrality. So, electrically neutral on the whole, but the neutrality may not be maintained over very small microscopic regions. So, there is a chance that at some point there are more number of electrons or ions. Okay. So, within this plasma particles, the electrons and ions move around because of their thermal energies, because of the temperature that is there. So, these particles can be moving around from one point to another point, and they may produce local concentration of charges. We know this, right? And when there is a local charge concentration, that means an excess amount of electrons, for example, immediately an electric field would be set up, and this electric field would make the electrons oscillate because of their thermal energy, and thereby the neutrality is established. At the same time, it also gives you the provision to understand the plasma frequency, right. Most importantly, something that we have to understand very clearly is that the plasma generally allows charge separation only to a certain distance, where there can be a balance between the thermal energy of the particle, let us say the kinetic energy because of the temperature of the particle, and the electrostatic potential energy. Electrostatic. So, these two energies when they are matched. So, that means if you are separating electrons over a particular distance d, so plasma can allow charge separation only to a certain value of d, where the kinetic energy or the thermal energy of these electrons is in correspondence or is approximately equal to the electrostatic potential energy. If it is very large distance, then the electrostatic potential energy is of course there, but the kinetic energy of the particles may not be sufficient to cover this or to nullify this charge separation, right. So, this is a limiting condition for setting up of plasma frequency, or for that matter the charge deviation from charge neutrality. So, we can say that plasma can allow charge separation only to certain distances, where or up to which there can be a balance between the thermal energy of the particles and the electrostatic potential energy which has resulted by the charge separation, right. And second most important thing is, as a result, plasma cannot maintain deviation from the charge neutrality over macroscopic distances, but it can only maintain, or it can only allow deviations from the local charge neutrality over a very small microscopic distances, right. So, this distance of separation or over which the charges are being pulled apart should be microscopic in nature, So, if you extend it beyond a distance, this deviation from charge neutrality may not be valid. Okay. So, in order to understand this concept better, so we mean saying that whenever you displace electrons, immediately electric field would be set up, and the electron will be asked to, or electron will be coming back against the direction of electric field to nullify this charge separation, right. So, in order to understand this concept, or the setting up of electric field, or how large are these electric fields going to be, we can take a simple example. Let us say we consider, so this is example number 1 for today's class. So, let us consider a uniform plasma with number of electrons equal to number of ions, which is of the order of 10 to the power of 18 per meter cube. And so, this is the plasma description, and let us consider a small spherical volume volume with radius r is equals to 0.01 meter. Okay. So, let us say we have a small spherical volume inside this plasma with radius r is equals to 0.01 meters, and within this volume we have number of ion, that is the ion density is larger than the electron density. How much? By 1%. Okay. Then we have to find out what will be the magnitude of the electric field that will be produced within this sphere. So, we have the plasma, and inside the plasma we have considered a small region whose spherical region whose radius is something like 0.01 meter, and only within this spherical region ion density is larger than electron density by 1%. That means, if there are 100 electrons in that region, the number of ions would be just 1 more, that is not 1 electrons will be there in terms of percentages, right. So, now you have to think about the total number of electrons, and then we have to find out how much amount of electric field will be produced by this charge separation, right. So, obviously, there are less number of electrons in comparison to the ions, right. So, number of ions in this case, the solution, the number of ions Ni is equal to 1.01 Ne. How much is it? 101% of electrons, right. 101 divided by 100 into Ne. So, the total charge density, let us say rho is Ne minus Ni times the charge. This is the formula, right. But in our case, it is number of ions is greater than number of electrons. So, the total charge is, it has to be total charge has to be written as Ni minus Ne, number of particles per unit volume multiplied by particle charge, individual particle charge. So, we will have charge per unit volume, right. So, if you want to find out the charge, then we have to see the charge can be 4 by 3 pi r cube into volume into the charge density, that will be Ni minus Ne times Q. Charge per unit volume is charge density. Charge is equals to charge density multiplied by volume. Since it is a spherical volume, the volume becomes 4 by 3 pi r cube, right. Let us take it to the next slide. I will rewrite the expression. Q is equals to 4 by 3 pi r cube into Ni minus Ne multiplied by charge. So, Q is equals to 4 by 3, the radius of the sphere is 0.01 meter cube, Ni is 1.01 times Ne, 1.01 minus 1 times Ne times Q. So, Q becomes 4 by 3 into 3.14 into 0.01 cube into 0.01 into 1 into 10 to the power of plus 18, charge is 1.6 10 to the power of minus 19. This is the charge. What is this? This is the additional charge, right. Now, the potential that will be created out of this has to be phi is equals to 1 by 4 pi epsilon naught Q by R. So, potential phi, the value of 1 by 4 pi epsilon naught is 9 10 to the power of 9 into q. Q is all of this, divided by r is 0.01 meters, right. So, that will be 4 by 3 into, I am just rewriting it, all of it, 0.01 cube into 0.01 into 1 into 10 to the power of 18 into 1.6 into 10 to the power of minus 19, right. So, if you use a calculator, what you will realize is that this will be, this entire product on the right hand side will be approximately equal to 6000 volts. The potential is 6000 volts. Now, the point that I am trying to convey is that the imbalance between the number of electrons and ions within the sphere is only 1%. The number of ions are larger only by 1%. That means electrons are displaced. How many electrons? Only 1 electron per 100 ions is displaced from this region, and they have been kept away only by a very small distance actually, right. And because of that, the amount of potential that develops is very high. You see, this 6000 volts is a very large value of potential, right. That means that, like we said before, whenever you try to displace electrons, immediately large electric fields would be set up, which will try to nullify the charge movement immediately, right. So, this is how we can understand the setting up of electric field by the displacement of electrons, and how plasma oscillations, a natural consequence of this, are relevant to maintain charge neutrality inside the plasma. So, plasma is neutral in a macroscopic sense scale, but neutrality may not be maintained over very small microscopic lengths and as well as time scales. Now, let us take one more example to understand concept of device length, or how the plasma criteria can be used to maintain or to qualify an ionized gas as plasma. Okay. Question number 2, example 2. Okay. Let us say for a typical fusion reactor, for a typical fusion reactor, the electron density is Ne is equal to 10 to the power of 21 per meter cube, and temperature is 10 kilo electron volts. Verify if this can be called as plasma, right. So, for a typical fusion reactor, the electron densities are of the order of 10 to the power of 21 per meter cube, and the temperature is 10 keV, right. Now, we know that we use the scale of electron volts for measuring or for quantifying the temperatures of plasma, where the equality is 1 electron volt is equals to 11,600 temperature units, that is in Kelvin. Okay. Now, of course, this is an ionized gas, no doubt, but should we call it as plasma or not? That is the question, right. Now, for it to be called as plasma, we require 3 conditions. 1, omega c tau p should be much greater than 1. Number 2 is the plasma parameter, the number of plasma particles or ionized particles within the Debye sphere must be very large. and the length scale of the plasma should be very large in comparison to the device length, right. So, let us start from the device length. Lambda d is equals to square root of epsilon naught kBt by n e square. We know the meaning of each of the variable or constant that appears on the right hand side. So, we can directly substitute. So, epsilon naught is 8.854 10 to the power of minus 12. kBt is the energy, right. So, temperature is used in electron volts. So, the Boltzmann's constant, which is should also be converted into electron volts. So, we can write it as 10 to the power of 4 is the temperature, and if you write it in electron volts, you have to write it 1.6 10 to the power of minus 19. 1 electron volt is equals to 1.6 10 to the power of minus 19 joules. N is 10 to the power of 21. Charge density is 10 to the power of 21. Electron charge is 1.6 10 to the power of minus 19 E square. So, E square. What is this? The units are meters. So, this will become 2.3 10 to the power of minus 5 meters. So, lambda d is of the order of this. What it means is that if you try to put some external electric field, this is the distance up to which the electric field can penetrate. Beyond this, the electric field will be invisible, right. But this does not guarantee the condition of plasma, right. So, we have to see number of particles inside the plasma is 4 by 3 pi lambda d cube into n, which will be 4 by 3 into 3.14 into lambda d cube. So, that is 2.3 10 to the power of minus 5 into 10 to the power of 21. So, if you do this, you will get 5.1 10 to the power of 7. What is this? This is Nd. Nd is called as the plasma parameter. So, you can see that the plasma parameter is very, very large, which means within the device sphere, there are a lot of charged particles, electrons or ions. So, conclusively, we can say that since this condition is valid, we can say that this particular ionized gas which exists within a reactor can be given the name of plasma, right. So, this is the basic idea. So, similarly, we can, using the formulae of lambda d or simplified formulas of device length, plasma frequency, etc., we can quantify whether a particular gas would be a plasma or not. One more very interesting problem that we can take is basically kind of a derivation, which can also be considered as an extension to the device length derivation itself, right. So, we know that the question number 3, we know that the plasma potential phi or the device potential phi of r is given as 1 by 4 pi epsilon naught q by r into e to the power of minus r by lambda d, right, where lambda d is the device length. If this is the potential, find out or derive an expression for the electric field. So, we know that electric field is the negative potential gradient. So, E is equals to minus del phi, see, minus del phi. We have to find out the electric field now. Okay. But since the coordinate system is in terms of r, we have to use an appropriate formula. So, we can write, the question is find the electric field. The solution. So, we know that the electric field E is minus r cap d phi by dr. Why? Because of this. You see this? So, we can write it as using all of this potential inside the bracket. So, we can bring out q by 4 pi epsilon naught r cap times, when we apply differentiation on 1 by r into e to the power of minus r by lambda d. So, it is d by dr of 1 by r e to the power of minus r by lambda d. The direction is already given, r cap. So, this is uv, d by dr of uv, udv plus vdu. So, that is what I am going to write here, minus 1 by r square e to the power of minus r by lambda d minus 1 by r into 1 by lambda d e to the power of minus r by lambda d. So, using the fact that r cap is r by mod r, we can write the electric field as q by 4 pi epsilon naught one by r plus 1 by lambda d e to the power of minus r by lambda d multiplied by r cap by r square. Okay. So, one out of this term and this term I have taken 1 by r common, it came out, and this r cap is r by mod r, which is again r, that is why we have r square outside and the remaining terms inside this, right. So, this is the electric field. Now, that we can simplify it further, and we can also find out what is the charge density, right. So, this is the electric field which is created by the within the device potential. So, we can also go ahead and find out what is the charge density, rho of r. Okay. Let us take rho of r. So, how do we know how do we calculate rho of r? We know phi, we know E, the electric field, the potential and the charge density. So, knowing potential, we have calculated the electric field. How can we calculate the charge density? Now, having known the potential, the electric field, we can now calculate the charge density by using the formula del dot E is equals to rho by epsilon naught, which is the first Maxwell equation. So, what I will do is rho of r, the charge density, is epsilon naught times del dot E. Using the electric field that we have just derived, it will be q by 4 pi del dot r by r cube e to the power of minus r by lambda d plus r by lambda d r square e to the power of minus r by lambda d. Okay. Now, we have to calculate the divergence of all this quantity which appears in the bracket. Okay. So, we will use a standard vector identity which is del dot phi a. if we have a situation where we have to calculate the divergence of a vector being multiplied by a scalar function, then the formula is del phi dot A plus phi times del dot A. Okay. First one is find the gradient, then take a divergence with the vector, then put the scalar quantity outside, then again you will get a scalar. So, eventually the entire summation is a scalar. So, the charge density rho of R is q by 4 pi. I will just write the entire algebraic expansion. You can do it without looking at the board. E to the power of minus r by lambda d times r cap by r cube plus e to the power of minus r by lambda d we will have 4 terms, because there are 2 terms within the divergence bracket, right. 1 by lambda d del of e to the power of minus r by lambda d r cap by r square plus 1 by lambda d right. Now, using the fact that del of e to the power of minus r by lambda d is nothing but minus 1 by lambda d e to the power of minus r by lambda d, and the direction would be along r cap, and del dot r by r cube can be rewritten as minus del dot del of 1 by r. Del of 1 by r is minus 1 by r cube. We are multiplying with r. So, the vector will stay outside, and then you will have, which will be equal to the same thing, right. So, which can be written as del square of 1 by r. We know that del square of 1 by r is 4 pi times delta for the Dirac delta function. Using this into this, we can write the charge density rho of r is equals to minus 1 by lambda d e to the power of minus r by lambda d to 1 by r square plus e to the power of minus r by lambda d So, simplifying all that, we will have, cancelling the relevant term, we will have q times delta r minus 1 by 4 pi lambda d square r e to the power of minus r by lambda d. This is the charge density, right. So, what we have done is, we have given the device potential, we are able to find out the electric field and the charge density, which is actually responsible for the shielding effect, right.